Okay. Welcome everyone to the third DWL workshop and its webinar series. Today we'll run webinar 3. Before we do that, I'd like to wish to acknowledge the people of the Kulin Nations on whose land we are gathered today, and I pay my respects to their elders past and present. I also like to acknowledge the Australian National Fabrication Facility, ANFF, for the generous funding and support, and especially its CEO, Jane Fitzpatrick. If you'd like to know more about ANFF, please have a look at the website anff.org.au. And lastly, of course, I'd like to thank the whole team for putting all the hard work and effort into it and making this webinar series and workshop happening. If you'd like to learn more about us and past events, please come and visit dwl.org.au. And with this, welcome to webinar number 3, the physics of lithography resists, presented by Scott Lewis from Caltech. And I have to pick up my cheat sheet. So short bio about Scott. Dr. Lewis has over 15 years of experience developing metal organic resist materials. He has also developed a 3D Monte Carlo simulation suite called Excalibur. So it's similar to Tracer, and we're going to hear much more about it and what it can do. He's a co-founder of a spin-out company called SGK Technologies, which delivers new ultra-high resolution metal organic resist technologies. And those resists exhibit very high aspect ratios of more than 10:1. And in November 2022, Dr. Lewis joined the California Institute of Technology, Caltech. And there he designs new active materials that can be integrated into electron and ion beam engineering systems. His research interests particularly are developing new models for 3D Monte Carlo simulations, developing new electron beam tools for additive manufacturing, developing new materials for electron beam lithography down to 5 nanometer feature sizes, developing pattern transfer processes, and developing electron accelerator technology that leads to the understanding of the exposure mechanisms of resist materials. Before joining Caltech, in 2016, Dr. Lewis was appointed to a research fellow at the School of Chemistry at the University of Manchester in the UK. He got his Bachelor of Engineering from Cardiff University in the UK, as well as his Masters of Science and his PhD in Electronic Engineering. In 2016, Dr. Lewis was a recipient of the Royal Society of Chemistry Emerging Technologies for Materials Award, and he's the author or co-author of more than 20 papers, 3 book chapters, and over 40 patent applications. So Scott also asked me to ask the audience those 3 questions. So can I kindly ask everyone in the webinar to please let us know if you use EBL? If you do you run 100 kV, 30 kV or below? And how many of you guys using Genesis Tracer? And with that, Scott, I'll hand over to you.
Thank you, Michael. Can you hear me?
We can.
Perfect. So I'll share my my screen, and I will play this. Just give it a second. Are you seeing my screen?
We can, but not in presenter mode.
Unfortunately, the bar is there we go. So right, here we are. So
perfect.
Thank you very much, Michael, for that nice introduction. Hello, everyone. As you can tell from my accent that I'm not American. I'm British. I've been working with Guy DeRose at Caltech for a few years now, and what I'm going to show to you today is some of the work that Guy and myself and my PhD students have been doing for the last 15 years or more. So yeah, this is, unfortunately, I've got a criticism of my own slides that are very busy. They're quite heavy. So we'll go through how to read them. I know that this webinar is being recorded. So you can go back and look at this at your leisure. So if we get into this. So essentially, when Michael asked me to present based on the physics of resists, how do they work, essentially what they are, why they work, what are the pitfalls, and these sorts of things, I kind of thought, well, how do I present essentially like 25 years work, in 2 hours? So essentially I started to do that, and we ended up splitting the content. So essentially what we're going to do today, I'm going to see if I can use a pointer. Right. Okay. So essentially we're going to do part 1 today. I'm hoping this is going to take about 90 minutes. My clock has already got running. And then we're going to do the second part sometime in March. Okay. So I'm going to basically run over scaling, why do we scale? Why do we need to do that? I think we all know why that is. So coming from a university background, it's very easy to do electron beam lithography because it's quite cheap. And I'll explain that in a moment. So the history of where myself have come from is when I'm developing these models is I can test the models using electron beam lithography, and it's very easy to do so. And what I've realized is that, you can have 2 camps. You can be in the 100 kilovolt tools, or you can have the 30 kilovolt tools. So I'll get into some of that. So we'll go into the electron scattering mechanics. Okay. And then what we will do then is essentially we'll use the mathematics and the physics that we've developed here. And then we will construct a high energy and a low energy electron beam scattering model. Okay, so how does it work? Why do electrons scatter and have the behaviors they have? And more importantly, what's their effects on organic in today's webinar? But more importantly for me, it's about what's happening in these inorganic materials. This is the exciting part for me. This is like the robust. So this is kind of like we will build this this model, then we'll go through like a single case. So we're going to do things by case studies. Okay, so what is a high energy beam? How does it behave in gold, for instance, or how does it behave in silicon? How does it behave in carbon? So you've got like the atomic numbers, and how does the atomic number contrast affect the behavior of the materials. Then I'm going to talk to you about resist design considerations. Okay, so when we design a resist, what essentially, how do we do this? And then of course everybody knows PMMA and ZEP. So I know that from Christopher Ober's webinar that most people are asking about how does this work. So I've got into some depth about how does this work, and then what we will then do is we'll call it a break there, and then we will do this in the second part. So scaling. Okay, so I'm not going to bore you with Moore's law. This is what it looks like, right? This is what the semiconductor industry is very interested in. We can see that these are the costs and the projection of the tools that have basically have come out of the semiconductor industry. So, we've got projection to GEI line that we all know in university environment, but, this is where we want to be. Okay, so coming from a university environment, say like University of Manchester, especially at Caltech today. So if I want to carry on my work, I can't work with photoresists, which are here. I've got to work in this area, okay, in order for me to get grants. So that's why my work predominantly is in EUV, which you'll hear next webinar in March. But you can kind of see that the cost is basically spiraling out of control. Okay, this is the main takeaway. I've been told as of 3 hours today that this is double now with high NA tools. Okay, so this is, I'm going to see if I can move this out of my way. So you can see that these are what the footprint of the tools look like. And then this is what the latest EUV tool looks like. So this is current ASML NXE 3300 tool looks like. Okay, so how it works. I know that Christopher Obo went through this, but I'll just do this very quickly. You have a tin plasma that you generate with it's like a vapor of tin or a drip of tin in a vacuum. You shine a CO laser at it, and then it emits 13.4 nanometer wavelength. I don't consider light in a wavelength. I always think of it in EV. Because I need to think about the transitions of what happens inside a resist, and I always think about the bonding energies and all this sort of stuff. So I was thinking in EV. So essentially, that these tools are very expensive. Now, ASML are quite lucrative. They're the only company in the world that actually can deliver this. This tool they will sell. I'm now told it's double that. But they'll also have a service contract on it, like you would with an e-beam tool. And that service contract is kind of like, every week you'll swap out the mirrors. You can imagine a tin plasma, and the tin goes everywhere. So if the tin covers the mirrors, then they're no longer going to reflect. Okay, meaning that these as I'm told, these mirrors get swapped out at $1 million a week. Okay, so that's like $52 million per year, and then they'll sell you that for 5 years cover. So I've had so this is one of these is in Albany, in upstate New York, and there's one in IMAC that we're able to get you to get on and experiment with. However, you can do this as synchrotrons. Okay, so I work in Switzerland because it's quite close to the UK. Not so much anymore because I've moved, but there's one in the ALS, which is in Berkeley University, and essentially they're well maintained to do this kind of work or this research. Okay, so essentially moving on. So the other side of the coin, which is a lot cheaper, is these tools. So these are electron beam tools. So you would kind of be used to this in a university environment. So essentially that we can get this, we can get like nanometer or sub 10 nanometer features off this with these. Okay, so how does it work? We all know how it works, but I'll just run over it very quickly. We have a zirconium oxide on a tungsten emitter. So the emitter is basically like it could be 400 nanometers wide, and it has different facets. Okay, so this is made of tungsten, and you have some zirconium around it, and then when you heat it up to like 2000 degrees, the zirconium essentially moves and it migrates to the tip, and it makes a virtual tip. So when people think that you're emitting between the interface from the tungsten to the zirconium oxide. So what it means is that you've got a work function, which is frightfully important because the work function of tungsten is like 4.5 and zirconium oxides about 4. So you're lowering that work function, okay, and then you're just emitting the electrons. Okay, goes into this suppressor, and then it sees the anode, and this is the accelerator. Okay, so we have a crossover point at these lenses. So when you have a crossover point, you need to do what we call spherical aberration. Okay, so this is where you need to sort your astigmatism out. We have obviously a beam blanker. So if you like put 200 volts across this, then your beam, instead of goes through, it just hits this aperture plate, and then that's how it blanks. Okay, so this is definitely electrostatic because you want it to happen really quickly. So this is when you write your patterns with, like, say Beamer or Alfie Quantum, depending on what camp you're in. Essentially, that this is your way how the beam parks itself, not in the middle of your right, because that would be not very good. You have a second lens, so you have another crossover point that you need to sort your spherical aberration out. Most of this gets blocked by the objective aperture, and you go into subjective lens, and then you get a very, very fine beam. Okay, so this is kind of like what you'll see in an EPBG or a Joule system, but for 30 kV, it's very different. It's made by an Einzel lens. So essentially what you've got is a lens inside a lens. Okay, so you've got your liner there. So you've got your acceleration voltage, which could be, let's say you want 10 kV. You have a liner for these type of these tools, so like a Zeiss column, if you've got a Zeiss SEM. So you have an 8 kV booster. So if you start off with 10, you end up with 18. And then you essentially don't have any crossover points, which is why it's very easy to get really nice and crisp images out of a Zeiss tool, because your only crossover point is at the surface, because your ray diagram kind of goes like that. Okay, and then you've got your lenses that basically pull out the beam, and then they just push it, force it. So your coils basically force the electrons together, and that's how you get a very fine spot. But there are other architectures, like you can see here in pink. So this one's kind of won out, really. So this is IMS nanofabrication, and they work at 50 kV. 50 kV is optimum, and you'll see why that is for a resist. And what they have is like 212,244 beams all working through an aperture plate. And you can imagine you've got some field plates or tracks, and you put a field across it, and you can move individual beams. Okay, so you can imagine like you've got like multiple beams coming through here. If you can have multiple apertures, that's what's going on. They can do, I think it's about 11 nanometer half pitch at the minute, which is really good. So these are types of different architectures. So I'm here to talk about a resist. So what is a resist? So you can read the definition. So essentially, it's a material that when you shine radiation or electrons, it undergoes a chemical change or a physical chemical change. Okay. So this radiation can be, light. It can even be daylight, actually. It's light, radiation. It could be 193 immersion all the way to EUV and beyond. Okay. Also going to be electron beam. So the whole point of a resist is, why do we call it a resist? Because it needs to resist some chemicals, because you need to transfer the pattern. Okay, so what do? We get a resist and we spin coat it on a surface, and this could be silicon, it could be gallium arsenide, it can be whatever you want, right? As long as it's a semiconductor. We get an electron beam, or this can be just light, and we write our patterns like so, which is represented in green. This is the green is basically showing there's a chemical change there. Okay, and we will go into what that chemical change really means. This isn't changed, but this is. So this means that this is still soluble. So this is what we call a negative tone I'm showing here. So this is all soluble in the solvent, and then we reveal this pattern behind. Okay, and then with this shower, I'm just showing not a wet etch, but a dry etch. So in my research, I'm not going to get any funding for wet etch design or anything like that. It's all about fine features. So if you want like 10 nanometer half pitch, you're not going to etch that with KOH or anything like that if it's a silicon processor you want. So we predominantly use dry etch. So that's like ions, really, so it's SF6, and I'll go into that a little bit later. And of course, we strip the resist, and then we're left with these fins that we can essentially shape the silicon rather, or the underlying substrate, and we can make devices from that. So we've got some lithographic materials. We've got, as I said, positive tone, negative tone. So going back, this is showing you a negative tone behavior. But of course, if I wrote this and then this broke down into smaller pieces, which is more soluble than this, than the material, then when we come to develop it, this gets removed. Okay, so it's the inverse of this process. So that's the difference between a positive tone and a negative tone. So we've got some categories. As I say, I can't get funding for anything for here, so I'm not even looking at that. We've got E-beam, it's very easy to work with. And then, you know, Guy DeRose at Caltech bought an ion beam, helium ion beam, 2016. I could be wrong. It's on that order. 2008. No, we published in 2018. So 2016, whatever. It's around all that time. So this is, in my opinion, is the state of the art. Okay, it's not this, and it's not this. It's this. So this is kind of like I can get like 5 nanometer half pitch without even trying. Okay, so this is brilliant. This is like you can do this with helium ions. I'm not going to show you this today, but if you're interested, I can put this into my slides in March, because this is the exciting part. Then we've got some photoresists. Of course, we've got visible, you know, H and I line. Then we've got ARF or immersion. We do have this F2. This never really played out. There was a lot of research that was done at the turn of the century, but this has problems with atmosphere. So to try and get the light to be transmitted through, you know, like air, yeah, good luck. That's not gonna happen. But the current state of the art for a photoresist is this. This is EUV. This is a wavelength of 13.4. Sorry, I have to think. I don't think in wavelengths, but 92 EB. Okay, so this is current state of the art. This went into production November 2019, I believe. That's when they started to make new devices like your FinFETs, and now they're into GAAs, right? So the gate all around architectures that they're developing today. So this material, you know, this is going to have an evolution. So we go from, you know, this has got like a numerical aperture. So a numerical aperture is basically how much of the light actually makes it to the resist. It's basically 0.35, but now ASML are bringing out high NA. So high NA basically is a high numerical aperture, and that's like 0.55. And now they're starting to do a lot of research into that, and that will be coming into play quite soon, I believe. And then they're looking into what they call hyper NA, which is 0.75. So that's more of the light. So it means your throughput basically increases. Okay. So that's why they do that. But of course, when they do that, the lenses are going to be more expensive. It's going to be, you know, the astronomical costs will just spiral out of control. Okay. So this is my bread and butter, I guess. This is what I look at. So this is like resist specification that I get told by ASML, this is what they need. Okay. So essentially the resolution is 12 nanometer half pitch. Okay. So if you're talking to like chemical companies like say Sumitomo or Dow Corning or you know, JSL Micro with Impria, if you know, this is the spec that they always look at. So we've got 40 millijoules per centimeter squared at this is hard. Okay. This is really, 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 really hard. Because when you go up in resolution, the dose actually goes up as well, because you're actually hitting less of the material because it's more fine. So it gets really, really hard. And then we have materials that can basically do this, and then these kind of drop off. So the line edge roughness, of course, is frightfully important, because if you want to make a track or a gate for a transistor, for instance, what happens is that if you've got a nice straight and then you've got another one, then the electric field between it, it remains constant. But if you've got something that's wavy like this, then where you've got your pinch point, the current that passes through will be magnitude, will increase, and it will turn into heat, and then the thing will blow. In fact, the gold just evaporates away. So this is getting hard as well. So everything you see here is getting hard. Spin speed. Spin speed is quite interesting. Okay, so being in a university environment, the probability of spin coating 300 millimeter wafers is pretty slim. Okay, I've never come across it, only in iMac. And I asked my PhD students, can you spin this? And when I develop a resist, at the beginning, we were spin coating at like 8,000 RPM. So of course they tried to do that with something like this big. You do that, it's pretty scary, because you get vibrations. This thing is spinning. It's like a big disc. So yeah, in my opinion, it's very, very dangerous. So we tried to keep things at 1,500 or less. So I tried to spin coat mine at like 1,000, maybe 800, but that depends on the resistor we're making. Okay. Now another industry standard. This is what makes things difficult, is this, because I have a resist that might not be soluble in these types of materials, in these casting solvents. So that becomes very difficult. Okay, so you could have this wonderful molecule that you've designed, maybe in tracer, or in my case, Excalibur. You go and synthesize it. It takes like a few months to synthesize. You've got to find a chemist that knows how to synthesize it. And you put it in the solvent of choice, and then it doesn't spin, because you put it in the solvent and it just sediments out. So your resistor is actually in the bottom of the flask, and that's disappointing. Okay, so this is what really makes things hard. Being in a chemical, I spent 10 years in a chemistry department, and in a chemistry department, yeah, it's not like a clean room. Okay, so getting this 5 parts per trillion is you need to go to a chemical company that can do that. So it's not like filtration, which I'll show you and talk to you a little bit later on, but this is really, really, really hard. But you need to work with people who know how to do that. And in a university environment, no, you're lucky if the students clean their glassware. This is also interesting. This is difficult as well. So the outgassing, what does the outgassing mean, right? So essentially you can put so when you spin coat your wafer, there's roughly about 12% of the solvent still left in. It gets trapped in the film. So when you put it in a vacuum, it just diffuses and comes out. Okay, but not always. So the problem with that is that you've got mirrors in an EUV system that are atomically clean, and now your resistor's outgassing, and those products, even though it's very, 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 very infinitesimally small, it ends up on the mirrors. So then when the light travels and hits the mirrors and gets focused, and then goes through them or gets reflected from the mask, then you've got problems. So yeah, this is really, really hard. So this is the kind of target you really need to meet. And of course, you've got developing solvents. So from a negative tone point of view, resist, then I kind of use the same developing solvents as the casting solvents. But why would I change? So yeah, this is like the industry spec, and I'm showing you the triangle of death. So the triangle of death is basically, well, it's as grim as it sounds, because what tends to happen from my experience, from what I try to do, is what is this? Sorry about that. So what happens is I try to go for resolution first. And with resolution, it's usually the LER is tied to the resolution, okay? And then the dose or the sensitivity I work on later. So the problem is that, if I go for dose, it means that I'm having a trade-off between the resolution and this. So we work within what we call a Z parameter, and that's governed by this equation. Okay, and that gives you how good your material is. So my good friend Yasin Enchenki at PSI in Switzerland, he worked on these resists. So Impria is the state of the art. HSQ we all know and hate, I guess. And Card, well, that's not helpful. That can be many different things. So yeah. So I know what this is. This is like a tin-based metal organic. This is also an inorganic. It's a silicon oxide, I guess. That's what it turns into. And yeah, this is so the takeaway from this is that this is really hard to meet, and it's getting tougher and tougher and tougher every 2 years. All right, let's get into the anti-electron beam interactions. So I'm going to have to apologize. My slides are very hectic and very busy, but you should be able to follow them. So I'm going to try and do this by case study, so we can just go through the motions. I'm going to try and run over things as well, if I can. But today, what we're going to study is like the effects of backscattered electrons. So in red, PE stands for primary electron, and the backscattered electron is obviously the BSC. So this basically flies around the nucleus and then basically comes out like so. So this is something that we'll capture. The second thing is probably my bread and butter is secondary electrons, like how are they generated and what is the scattering angle and how do these affect the materials. So we will study this, and then this is really interesting. This is the Augers. Okay, so we will talk about Augers, but not in this because I'm not going to have the time to do that today. But we will do this in March because this is more exciting when you're working with metals, because you can imagine, like, if you're working with PMMA, ZEP. I mean, ZEP's got chlorine, but it's not that interesting. Where in metals, like let's say you're working with uranium, which I've made uranium-based resists, or gold resists, mercury constantly, because mercury is very, very nice. It's soluble in most things because it's already a liquid. So you can imagine you've got all these different transitions of where the electrons can be, meaning that a primary electron can come in and it can excite the atom and pull out these Augers. And then what, to my surprise, is I can tailor this depending on what atom is scattering off, that this can count for 50% of the exposure. So for EUV, that's great because it can come to me. So yeah, that's great. What we're not going to do is essentially generate X-rays. Okay, that's we'll save that for another day. But yeah, and the probability of generating X-rays are quite small compared to these guys. So we'll concentrate on these. Right, as I said, my slides are busy, so I'm very sorry about that. But the main takeaway really is the first thing that we're interested in is we need a scatter. Okay, so the electron comes in, hits what hits the atom, and these dots are represented for electrons, let's say. So I need to point out that electrons are pretty small. Okay, so the atom is pretty small, but it's like 10 to the minus 10 meters. Okay, so what I mean by that is, like, we've got a nucleus, protons, but we've also got a hell of a lot of free space in here. Okay, so the probability of this colliding with an electron is not impossible, but it's pretty unlikely as well. So what is happening is that in the physical sense is as this collides, this produces like a field or a wake. What I mean by a wake is if you've got a lake, and the lake, there's no movement in the water, where you have a speedboat and the speedboat races across the lake, it produces this wake behind it. And if we say that's the field, and it's that basically dislodges this, and that's what is the interaction. Okay. So essentially, what we need to calculate to see if this happens is we need to understand what the probability of causing a collision. I've got particles written there, but it's electrons. Okay. But in later, we'll talk about ions as well, or what the chemists call free radicals. So Rutherford, you know, he did a very good job. This is called the elastic cross section. So this is basically the probability of an interaction happening. Okay, so this is the equation. So what I'm going to say to every single one of you is today I'm not interested in deriving these things or where these things come from. I want to use them. I want to show you how they're used and how you can build up your own models. So if you're interested in finding out where these things come from, I do have references in here, but not on this slide for some reason. But there I have PhD students that you can download their theses and you can read where they come from. But I just don't have the time today. Okay. So essentially this slide essentially tells you how this equation works. Okay, so we've got the elastic cross section, we've got the atomic number, which is an interesting variable, because at a later date in March I'll tell you how we'll work with that, because you know, if you've got something like PMMA, it's made up of many different atoms. So how do you get an atomic number of that? It's what we call the effective atomic number, but we'll go into that later. We've got the energy, and then we've got the screening factor, alpha. So the screening factor is basically the electron cloud, is what I've tried to represent here. So this is, you can imagine this is the electron cloud and the probability of the scattering from that. We've basically got the units of the mass energy, because you can imagine we've got mass of the material, and we need to understand what that collision is. Okay, and it's kind of governed by this. But you can imagine for electrons, it's going to be relatively small. Okay, so essentially that's how it works. And we've got the screening factor, which is given by this. So you need to essentially work this out in order to plug that in. And yes, I will move on because of time. Okay, so we now have the mean free path. So we've basically had a scatter. Okay, something's happened. We don't know what yet. I'm going to move myself on this side, and the electron essentially, as this elastic scattering, is basically moving on to the next atom. Okay, so it's this distance, if you can see where my pointer is, to this distance, that is the mean free path. And then we calculate, we'll calculate that, and you calculate that, and I'm going to move, this is going to get interesting, moving me back and forth. It's governed by this. So this is the molecular weight, this is the Avogadro's number, this is the density, and then this is the elastic cross section, which we just went through. Right, so this is very difficult. Let me explain why. Because if I'm making a molecule, how do I know what the density is? Okay, measuring a density is very difficult. We usually do this by X-ray diffraction. So most of you would be like, X-ray diffraction, you need a reciprocal lattice to do that. So that's why we make crystals in order to do that. So we can make, so I work with a chemist that could make like crystals of the stuff which is this big, put it in an X-ray diffractometer, basically take the data over the angles, and then we can work out what the density is. But of course, that's in a solid, which is kind of what we want. But when we spin cast things or put things down or put the resist down dry, which is what the state of the art is now. I mean, for me, the last time I spun a resist would have been like 5 years ago, possibly. I mean, Guy will tell you. So what I usually do is sublimate it, and I'll go into that in a minute. So essentially, this is interesting, right? So essentially, the bigger this mean free path, so the larger the mean free path, the less scattering that goes on. So you can imagine, and we'll go into this in a minute, that as this collides with this electron, then what happens is it strips some energy. But of course, if it's large, if this distance is large and this atom is massive, then, well, you've got a large molecule, there's less to scatter off, then it leads to high resolution. And we'll get into that in a minute. So essentially, these are the references if you want to find out. I knew I put them on this slide somewhere or another. You'll see these throughout, but you can follow these, no worries. And of course, you can get my PhD thesis, my PhD students' theses off the web. So yeah, that's how that works. Okay, this is really important. This is the stopping power. So you can imagine that the electron has an energy. Let's say you've got a 100 kilovolt electron. It gets accelerated towards your resist. It collides with the resist, and something happens. So what happens is it needs to take some energy away from that because it's interfered with the outer shells, or the shells of your atom, and it's governed by this equation. Okay, so this equation is really important, but it also gives problems. And this is why I have this characteristic. So again, I'm moving myself. Sorry about this. So you can kind of see that this is linear. I know there's a bit of artistic license here, right? But this is essentially linear, and then we've got a cutoff. So what this means is that the model I'm showing you right now is good from 0.1 up to 500 kilovolts, a couple of megavolts actually, because of the linearity. So that means you can trust it. The problem is when you get into this regime, then you need a different model. And we're going to discuss that. So this is a low energy electron behavior. Now, it's a huge problem for the industry, right? Because, we've got, this is in kV, this is 100 volts, and EUV is 92. So it means that this model I can't use, okay? So I can only use this. So we'll go into this. So essentially that this is the equation. This is basically what we call the stopping power, okay? Right, ionization potential. So this is the equation that we use in order to find out how much interaction there's been and how much energy to strip. Okay, so we've got the atomic or the effective atomic number, but if it's just like a one species material, this will work fine. Okay, so essentially we can plug this number in, and then we can then essentially put it back into the stopping power, which you've just seen on a previous slide, and then you've got the whole package, right? So you know how much energy to strip from the electron. Okay. Of course, now we've got so essentially we've got the probability. We've got the probability of the interaction, which is our Rutherford scattering. So this is still elastic scattering, by the way. We know what the mean free path is, so that's the distance between the atoms. We've now got the stopping power. Now we need to understand what the scatter. So how does it scatter from one point to another. So we're looking at this scattering angle here in theta, and then we've got the azimuthal angle in phi. Okay, so the way to read this slide is this is the scattering angle, and this is the azimuthal angle. And again, I'm going to move myself out of the way. This is going to get tedious. So essentially, this is the equation that we need. So when we model things, it needs to be on a random number. It needs to be in a random event. Okay, so this is why we use this random number. Okay, so we have it in here. So and basically, this is a complete random process. And there's a bit of a caveat to that. So if you use Tracer or Casino or Penelope or any others, there probably are others, if you're going to do a point spread function to do your error correction, you use 1,000,000 electrons or you use 2,000,000. So, but our doses are quite low. So why do we use 1,000,000 electrons? And the reason is because a random number, if you're computing a random number, well, it's computed by, or the algorithm to compute is done by human beings, meaning that, okay, so if we're doing it, how random is a random number? So that's why we have, that's why we put a lot of electrons in to get over the statistical repeat of the model. So essentially, going back to this slide, this is the scattering, and this is the azimuthal angle, and that's all you really need to know. I mean, you can read this in your own time. It'd be quite boring if I read that out. Right. Okay. So we've done the elastic scatter. Now we need to understand what the inelastic scatter is doing. So the inelastic is basically the probability of generating what we call a secondary electron. Okay. This is what is the bread and butter. Okay, this mechanism does the exposure. So most people think, oh, it's the primary electrons. They go through. You'll find out that your resist is so small or thin in thickness that the interaction is quite low, meaning that the electrons, say if you're 100 kilovolts, they just fly through. And the inelastic scatter of when something takes place, the energy change is dramatic. Okay, very dramatic. So what this essentially says is that we need to determine what the inelastic scatter is, and it's governed by this equation. I'll go through this in an example. So I will unpick this for you. And we can go through it. This is why I'm kind of running over over these equations, because, you know, if my old professor at Cardiff University was like, oh, we can, you know, this is how we do it. I mean, I've had to develop this over like 20 years. So I'm trying to give it to you in one go, that you can just follow this at your leisure. So essentially, this is the equation that we need. Then we need to find this the scattering angles, which is governed by these again. So we've got the scattering angle, we've got the fraction of energy, which is frightfully important. Okay, so the energy you can imagine like as the elastic scatter, right? So the electrons in transmission mode. Okay, so as the electrons going through the resist, that's what we call transmission. Okay, so the amount of energy that's being taken from that is very, very small. Where when you generate a secondary electron, you go from, say, let's say you've got 100 kilovolts electron, you can generate secondary electrons with energies less than 1,000 volts. Then you can see that they behave. Then they will start to cascade and behave like primary electrons or the elastic scatter, but their energies are much smaller. So their interaction increases, meaning that the stopping power needs to be really high in order for a very fast resist to happen. And we all go through that. I know that's quite a lot to take in one go. So we've got low energy electrons. So I've just described the high energy, and now we're going to do some quantum mechanics. And this is, I formulated in a fairly easy methods to use and to follow through. Okay, so as I've said a few times, that I work at Caltech now. I've got students. I was at University of Manchester. I taught there for 15 years, so I had students. So to do a low energy model, I needed like master's degree students to pick it up. So I essentially just chose the quantum hard sphere approximation. There are hundreds, probably thousands of different models. Okay, so every time I go to three beams, or if I present at SPI advanced lithography, I always say the same thing. You know, if there's hundreds of models, are they all right? Are they all wrong? You know, what's going on there? Why are there so many? And to be fair, the one thing that I've learned over this time is that the modeling doesn't really matter. It's basically interpretation of what's happening, and that's the important thing, is the takeaway of what's going on. And you're going to see this as we progress, because the numbers that fly out don't really matter. It's the correlation between one material to another, but how you change that material. So if you change one atom, for instance, then you're able to normalize it. So when you go to test these like a synchrotron, or test them in E-beam, it's very easy to do. And then when you do things like that, you can actually correlate electron beam to EUV, where no one thought that was possible, but we're able to do that now. So yeah, let's jump back into this. So we've got this scattering cross section. So we need to get this cross section for in a quantum. So this is kind of like electrons that are behaving waves. So these are your orbitals. Okay, so these are your S, your D, and your P, and your F. And your scattering cross section is basically governed by this equation. Okay, so it's pretty easy to plug into like Python or something like that. Your wave number is governed by this, and your you've got the mass of the electron, the energy of the electron, Planck's constant, blah 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 blah. And essentially, what we do, we just sum them together in order to work out what this is. It's relatively straightforward. Okay. All right. So then again, we need to understand what the low energy scattering is, and the angles in your Smoother angle. Okay, so this is a little bit different because you need to work with S wave scattering and P wave. So there's like partial waves, and essentially it's just governed by this equation. And again, usual suspect is the same. Okay, so these are the two equations that we need in order to find the values to plug into, in my case, Excalibur, but you can write your own. All right. So the electrons stopping power is a lot easier. It's these are the equations are quite small. Okay. So essentially that we need to know the energy transfer, and it's basically done on a random number again. And these are what we essentially plug in order to find out what the energy of the transfer is to the new secondary electron. All right. Okay, so I've gone through very briefly the equations that we need to use. Now we're going to build the model. So I'm going to do something quite ambitious. We're going to build the high energy, and then we're going to build the low energy, and we're going to basically blend that together, okay, and see what that looks like. But we're going to do this for a single atom. Otherwise, I'll be here all day. So essentially what we need to do, we need to understand what an electron random walk is, okay? So you can imagine like the electron comes in and it just scatters off stuff, and we call this a random walk. Okay, so what we will do is, like it says there, we'll describe the problem. So we've got like in this case, it's a two-dimensional, the way I'm putting this, but in reality, it's three. On the next slide, I'll introduce the Z coordinate in so you can see how that happens, or how we approach that. So essentially, we need to find out what this scattering angle is, and this is by our usual suspect. So we've got X and Y, and we need to find the next step, which is Xn and excuse me, Yn, which I've labeled. Okay, this is the step. So this is the distance from this, or what we call the step length. So we've got this angle, and we're going to need to work out this angle. Okay, so the first angle is governed by this, and then we can find out the other angle, which is governed by that. And then we need to find the coordinates of the next step, which is in this position, and it's governed by this. These are what we call cosine directions. Okay, so we've got X, which is, or X or Y, which is the initial. We've got the step, and then we've got the cosine of, in this case, this guy, and then of this guy, right? So essentially, I'll go through this in a bit more. This is what we need in order to find out the next. Okay, so now we've got the cosine A and the cosine B, which are the cosines, so we can work out what we need to do in order to get to the next step. So this is governed by XY to CX and CY. So this is a notation that we use in the industry. And then this is the coordinate system. So this CA and CB is governed by these equations. Okay. And essentially, when we want to go, let's say with this diagram, so we go from XY to YN and XN and YN. What we then do is say, right, we'll reset the coordinates, and then these are the new coordinates, and then we go again. It's as simple as that. Okay. So this is for the elastic scatter. Okay. So essentially this is the algorithm that we use, right? And I've got the equations that you need in order to compute this. So we've got our starting coordinates, or our start and the starting direction, because they're equal. We need to find out the deviation of theta, calculate the new directions, which is governed by, I need to move myself again. There we go, which is governed by these two equations. And we'll go into this in a bit more detail. And we need to find a new direction, which is essentially these. And then we need to understand what the step length is, which is governed by this equation. Okay. So, and then when we want to go to the next one, we just loop it. We put this in a loop, and that's what we do. And of course, this is all governed on a random number, and the random number basically dictates which way the angles are and which directions that it changes. So the probability of one random walk to look like another is pretty slim. Okay, so now we're going to put some real physics into this. Okay, so again, I'm going to move myself. So this is the starting place, the starting point. We've got X, Y, and Z. So I said I would introduce this. And then we've got this scattering angle. We've got Pn, and then we've got Pn plus 1. Okay. So we need to understand what this azimuthal and this scattering angle is, and the step length. So what we need to do, I'm going to go through this now in a little bit of detail. So essentially what we need to do is find the Rutherford's elastic cross section, which is basically the probability. Okay. So we find this out. Okay. So we need to understand the screening factor. So really speaking, we do this first. So this should have come first. Yeah. Find this. Then we need to find the mean free path. That X is meant to be a multiplication sign. So you multiply it all out. The parameters are basically given here. We need to find the step length, which is given there by this. So we need this, and then of course it's by a random number. And we find the natural log of that. And then now we've got an event that starts here. So we find the theta, cos theta. And this is the biggest takeaway of this. So if you've got high energy electrons, then the scattering angle is quite low. It's between 1 and 4 degrees. Okay. Actually 0 and 4 degrees. So essentially that it's the larger scattering angles which come from the secondary electrons and the OJs, because they've got low energy in order to cascade through the or travel through the material. So once we found this guy, we can then find the azimuthal angle, which is governed by this, and then we need to find this. Okay, so this is where it gets a little bit more tricky. So we need to find out what CA, CB, and CC is. Okay, so as I said, I'm not going to derive these. I'd be here all week if I did that. So essentially, we're just going to use them. So this is the final equation that we need in order to find out, in order to put that in here for the next step. So we need to find out what V1, V2, V3, V4 are, and that's governed by these guys, and we can just work this out. AM is governed by this, and this is the square, so that's not an X, that is a multiplication sign. And we can just plug these numbers in, okay? So once we've got these numbers, we can then plug this into this. And then this is the initial. So when we're starting off, this could be 0, 0, and 0. But then when we go to the next step, this is the value at that point, okay? Once we've got CA, CB, and CC, we can then plug this in. We've got the step. I'm going to move myself again. We've got the step length, and then we've got the initial coordinate. Okay. Once we've got that, we need to understand this. So we need to basically plug in the numbers into this, and then we can then strip the energy away from, or the energy loss away from the electron, and that's that. So that's the elastic scatter, and then what we do then is repeat this. So essentially, that's the elastic scatter. This is what we use, and I'm going to go through some. I'm going to go through an example. So this is like a case study for us. So I'm going to go through use it as a case study for copper. So I'm going to move myself once again, and these are the parameters that we start with. Okay, so we've got the atomic number, which is easy, so it's 29. So we've got the atomic mass, which is 63.5 grams per mole, and we got the density, which is rather nice, it's 8.9 grams per centimeter cubed. I've chosen an initial energy of the electron to be 10 keV. So you can imagine you're imaging copper with in an SEM, for instance. So we're going to do 2 steps. Okay. So the first step, we're going to have a random number. We're going to assign it 0.8. So the random number is a number, maybe I should have said this before, it's between 0 and 1. Okay. And the second is 0.45. So essentially, we calculate the screening factor, which is this. So I go through the numbers there. We calculate the Rutherford scattering cross section, which is governed this. So it's quite small. We work out what the mean free path is, which is quite small again, 26.25 angstroms. and then we calculate the step length. So that's that's the distance between the atoms, and you can see it's rather small. We'll work out the scattering angle and the azimuthal angle. So this is governed in radians. Okay, so that's important. So these are the numbers. So it means that we can plug this into these equations here. So we're going to start at 0, 0, 0. Why not? So of course, which means CA, CB, and CC are 0 as well. So we have this number, which is going to be 0. And then when we plug this in, it turns out to be 1. So we work out V1, which is this number, V2, which is 0, V3, which is nearly 1, and V4 in this case is 0.1. Okay, so then we need to work out what the CA, the coordinates for the next step, because we already know the coordinates already, which in our case is 0, 0. So we basically plug these numbers in, and we get 0.27, 17 rather. These are the numbers, and then we can basically plug this in. And again, I'm going to move myself out the way. So we can plug these numbers into this direction cosine. Okay, so to get the next coordinate. And essentially, not a lot happens. It's quite small. Then we need to work out what the stopping power is. Okay, so we work out the excuse me. So we work out the ionization potential, and as you see, it's not a lot. This is in kV. We then work out the stopping power. Okay, so you can see we've got a massive stopping power, but then you need to take this away from the energy loss, and the way we calculate that is that's meant to be the step, not the. So that's a mistake from me. That's just basically the step length multiplied by this stopping power, multiplied by the density, and then we've got a scaling factor here. Okay, so as you can see, when we plug these numbers in, this is not a lot happens. Okay, so you wouldn't expect so, because even though this looks like a long line, when we plot that, that's actually quite small. These distances, this is in angstroms. Okay, so basically not a lot has happened. Right, now we're going to do the next one. So we need to do the next step. And again, I'm going to move myself out of the way. So now we've got a new energy, which is governed by this. We have the new random number, which I've assigned 0.45. That was just random. Then we plug these numbers into the screening factor, the Rutherford, and you can see there's not a lot of difference of change from what we had last time, and I wouldn't expect so, because this is not, this is pretty close to 10 kV. Okay, so not a lot has happened, and again, we're on the same order of magnitude or the same order of number for the mean free path. And again, so I wouldn't expect this to be too different. And of course, now this comes into play, which is why this is a lot longer. This step length is longer, because this number is different. Okay, so the last one I believe was 0.8. This is 0.45. So we find the scattering angle and the azimuthal angle. So you can see these have changed. Now we've got our starting coordinates. So it's no longer 0, 0, 0. It's what we've just calculated. Okay, so these are the step lengths. Okay, so now we go through V1, V2, V3. So you can see these are very different. And then we need to plug these numbers into these into the new coordinate system. And then we get something which is a little bit larger. Okay, so now you can see in the graph, in the next, you can see we've got a lot, a bigger step, like so. Then we take, because the Rutherford scattering, there's not a lot has happened, right? The energy's not it's not a lot has happened, so I wouldn't expect these energy losses to be massive. Okay, so you can see that the scattering angle is very, very small. And again, right, this is a mistake. This is meant to be E step, not SF. So SFE stands for fast secondary electrons. So we'll see this in a minute. So I've just carried this over. That's why it looks like that. So this is just meant to be the energy of the electron, for the step of the electron. We multiply this out by the stopping power, which is also large, by density, so that stays the same. Oops, I don't know why I did that. And then we've got the scaling factor. So not a lot has happened. Okay, now we're going to calculate the inelastic. So the inelastic is what changes the solubility of your resist. So this is the one that's key. So you want a lot of these to happen within your resist. But again, if you have too many, they can have the energy that they can travel outside of your right your right field, or the pattern that you want to write, and then that's why your pattern gets wider, or your structure, the pattern of the structure you want gets bigger, and it's because of this, what's happening here. So let's jump back into this. We've got an atomic number of 29. This is all the same. I'm now using 10 keV because I'm at this point here. I've used the same random number. I could have changed that. So I need to work out, has a secondary electron occurred or not. So we need to work out the mean free path. So we already have this because we worked it out last time at that position. So the one thing that is beneficial, especially for speed, when you're computing these things, what I tend to, the philosophy I use is that we go through the model and we generate all our elastic scatters. So we follow all the trajectories. But when we cause a secondary electron, I save that in somewhere else in memory. And then once I've done all the elastic scatters, I then bring back those points and those energies, and then we just follow it through. And this is how we do this. So I work out I calculate the mean free path of a secondary electron if it's produced, and then I work out what of these things together. Okay, so you're seeing this for the first time. This is an equation that we use. This is the mass. This is the energy. This is a scaling factor. This is the density, and then this is the atomic number. So you plug this in, and then we need to find out what the third mean free path. So you're like, how is there 3 mean free paths? But I'll explain in a minute. So essentially, we calculate this. And then what we need to do is understand what the probability of generating a secondary electron is. Okay, so what we've got is we take the quotient from this. So if this is higher than this, then we're about 30% in this case, because we need to subtract it from 1. So essentially, it's not a great probability of generating. We normally look at like much higher than that, but for this purpose, I'm going to say we did strike one up, because it's not impossible. Otherwise, we wouldn't be able to go through this, right? Essentially, once we've understood that a secondary electron could be generated, now that we go through the process, so we need to understand what the energy of this electron is, and it's governed by this. So essentially, we have this equation, and we get an energy of 0.625, and of course we need to multiply that out by the incoming energy, and that's what the energy of the secondary electron is. So it's just over 6 kilovolts in this case. It can be lower, it could be hundreds, okay? But of course, I wanted to make sure that we've got something decent, that we don't go straight into the low energy. I wanted to go through this. So essentially, we need to find out what the initial scattering angle is coming from here, right? Where, you know, what angle that is, and we're working that out as like 68.2. And, you know, we've got the azimuthal angle as well, and that's about 2 degrees. So it's 2 degrees this way and 68 degrees this way, which is about right. I would expect them to be between 80 and 90, but in this case, it's 68. Not impossible. It does happen. So yeah, once we found these out, we need to find out how to generate this new coordinate. And once we've got this, we can just start saying, well, it's an elastic scatter. So we go through the entire process again. So we calculate the screening factor, which is govern this, and this is now of the fast secondary electron. So that's that energy of 6.25. And then we just plug in the numbers for the Rutherford scattering cross section, and we're governed with this number, and then we calculate the mean free path, and that's governed by this number, and then we understand or calculate what the step length is. Wait a minute. So after that, we calculate the scattering coordinates for the next step. Actually, no, we don't. That's not true. We basically need to calculate. Yeah, we do. So we calculate this, the AM, and we got V1, V2, V3, and V4. We calculate these. Now we've got the starting coordinates for this. And then we can basically pull this out, which I've got CP. In fact, I haven't written it. It's this. So it's this number. And essentially, we work out what our scattering CC, CA, and CB is the same. And then we work out what these numbers are down here. So these are a lot bigger because the energy is a lot smaller. A lot smaller. So then we work out what this is. So this is not going to be too much of a change. So for the ionization potential, we work out what our stopping power is, and then we work out the energy loss. And because there's an elastic scatter, not a lot happened. So then what we then do is follow this through again, and to see if we scattered or generated a secondary electron, and it repeats like millions of times. Okay. Right, let's do the low energy secondary electrons, which is governed by this. So now we've got new coordinates, which is governed here. So this is where we're at. So, you know, CA and CB is basically this. I've chosen this arbitrarily. So it's like, let's call it 50 EV. I've chosen a random number of 0.35, and then we need to calculate this this Thomas Fermi's radius. Okay, so we need to work this out, and I've given it here for you. We need to work out what the wave number is for K, and we need to convert things in from joules. Work out what the wave number is, and we're given that in meters, and then we need to work out what the product is, which I've calculated here for you. We need to put this in the terms, so we need to collect these terms together. So to calculate the cross section. So I've governed it. I've basically done this for you, and of course, for 7, we don't get any. So then we just basically do this. So then we get the scattering cross section. As you can see, is a lot smaller. And we then calculate the mean free path, and the mean free path is governed by this, not what we calculated earlier. Okay, so mean free path is a lot smaller, and of course we need to govern that, multiply that out by the cross section, and this is what we get. We need to calculate the scattering angles. So again, this is the same suspect, and then we use this this formula, and we basically pull this out. We need to calculate the new direction cosines, and I've done that for you. And here we are, so we can work out what they are, and then we can basically plug them into CA, CB, and then work out what the new position is. So the new position is, as you can see, is not, it's not a lot in it. So as you can see, it's very small. And then we just calculate the energy loss like we did before. And essentially, we've gone from 49.6 to 41.3. Right. Okay, so that's the maths. We've gone through an example. Now we need to understand what's actually going on when we put 1 million electrons in a material. So I'm going to start off with the one atom material. So we got gold, zirconium, silicon, and carbon. I've done that because we've got an atomic number of 79 and we're going down to 6, and zirconium is more or less in the middle of these two guys. So this is 100 kilovolts. You can see that we've got a density of, for gold, 19.3, which is quite light. It's not the largest, but it's up there. And you can see that, you know, for carbon, depending on what type of carbon, you know, amorphous carbon, you know, whatnot, but we'll get into that later. You can see this, it's much different. Okay, so it's much smaller. So you can see that with the high Z material, you get a lot more secondary electrons, a lot more things happening. You get a lot more of the spread of the beam happening within. I mean, this is a micron thick. Okay, so I know we don't expose resists at a Guy and I actually used to make resist which 2 microns thick, but that's a different story. But yeah, we usually, you know, within 50 nanometers, 100 nanometers thickness, or in my case, anything like 20 to 15 nanometers. So essentially, you can see that the effects of the atomic number and the molecular weight and the density has a huge effect, and you know, you can get your beam can be much finer with low Z materials. And that's it. I mean, your mean free path is much bigger here than it is there. So the collision is going to be a lot more here. 30 kV. So if you're imaging in an SEM, or if like me, you write resists at 30 kilovolts, you can see that you do get a spread, but you also get a penetration depth, which is a lot lower with high Z materials than say with carbon, or you know. So you can see the difference. So I'm just going to push on because I can see time's running away from me. So we've got 10 kV. You can see that the penetration depth is a lot lower with high Z materials. So there's a lot more going on, which is why in an SEM you see more. Okay. And then 1 kV, no surprises, penetration depth is even smaller. So if we look at this, I'm going to move myself once again. You can see the difference with these parameters, how we use them and why it matters in resist. So in resist, like say PMMA or organic, you're in this regime, where if you're in metal organic, you're in this regime. You know, these are sort of things that we can work with. All right, here we go. This is important. So I've shown this many years. for many years. This is the knobs or the parameters that I play with. So we've got the atomic number. So you've seen the effect of this now. So, you know, the sensitivity goes up if your atomic number is increased. So like, let's say gold, because you've got a lot more electrons in the outer shell, the probability of scattering from them is going to be a lot higher. Unfortunately, if you're generating a lot of secondary electrons, they're going to travel laterally because of that scattering angle is like 80 to 90, but in our case, when we did it, it was 68. So the scattering angle is not this way, it's this way. So it needs to come up this way. So essentially, your resolution goes down. So it's kind of like a trade-off. So this is dependent upon what the density is of the material. So if the atoms are a lot closer, so the density is higher, it means the probability of the electron when it scatters, it can collide with the with electrons in the adjacent atoms. So you can generate a lot more secondary electrons out, which means that your resolution goes down again, but your sensitivity goes up. And then with molecular weight is an interesting one. So if you've got a big molecule, so I design molecules that have a large space. So they're like a nanometer, maybe 1.5 nanometers in a circle. Then in the middle, I've got free space. So that means the electrons just can pass through that. So I can control the scattering angle from that. So it means that if you've got big molecules, then you're essentially going to not going to have a scatter, so you just pass through. So you can control your resist or your resolution that way. So we've got this arrow. No, it's a line. Sorry. We've got some numbers on it. What does this represent? We've got 0 down here, and we've got 9 up there, and we've got some solvents. This is the index polarity. So this is what I use when I understand what the casting solvent is. So when you're working with organic materials or inorganic, they need to be solubilized. You need to be able to spin coat them, and that's very difficult. Okay, because you're constantly battling these numbers. So when you're doing that, you need to figure out, will your molecule actually be soluble and not a suspension? Because the last thing you want to do is basically make your resist, and then you've got a sediment of molecules at the bottom of your glassware. So these are the material properties that I always consider. Material solubility is very, very, very important, because that goes, so it allows you to spin your resist or spin cast them, but it also allows you to develop as well. So with an electron beam, you're actually decomposing the molecule. So if you're breaking the molecule up into smaller parts, it's going to become more soluble. If that's the case, and it becomes positive tone. If you're breaking the molecule up into small parts, and that's decomposing into something that's no longer soluble in your casting solvents, but all the material around it is still unchanged, you spun cast that with a solvent, then all the outside can be washed away. So that becomes negative tone. So as I said earlier, I haven't spun a resist in like 5 years, or maybe even more. So I basically put a resist in a crucible, and I heat it, and then it sublimes, or you might think of it as evaporation. So it goes down dry. So your wafer is up here, and you sublime it, and it basically coats, you rotate, just like you do a metal evaporation. The difference is the molecule doesn't go into a liquid phase. It just goes from solid to gas phase, and then condenses on the wafer as a solid. So what you had in the crucible and what you have on the wafer is identical. Now, the beauty of doing that is, when we talked about impurities are problems. So when you spin cast your wafer, you could end up with impurities or like comets in your film. When you do it this way dry, that's not possible to happen. So you end up with a complete mirror. And the reason for that, because your impurities, they will sublime at a different temperature, or they will decompose in the crucible. And then you then get phase separation between your impurities and the resist, and the resist basically sublimes, leaving all the impurities left in the boat. And it's a very nice technique, and it's very pure. Atmospheric conditions, yeah, this is very problematic, especially for resists like metal organic, because air, they can attack. I worked in Manchester. I'm from Britain. It's a very, very rainy country. So water from the air can basically attack the resist, and so it starts to, in my case, etch, or it starts to write. So that is problematic. And then the other thing I consider is obviously secondary and OJ electron generation chemistry, such as amines, alkenes, pyridines, and carbonyl chemistry. We'll discuss that in a minute, and I'll show you what these things are. So one of the design rules are, the more the secondary electrons, like you can see what their effects are, the more of these electrons you generate, the more sensitive it's going to be. So that's the rule of thumb. Problem is, if you generate too many, your pattern fidelity just drops off. So it becomes a trade-off. Okay, so I'm going to go through the case study. I'm going to do this a bit fast because I'm running out of time. All right, so we're looking at monomer design. Okay, so this is PMMA, obviously, and this is ZEP. Okay, so if we can ignore these chains and we just look at this characteristic for once, yeah, that's what this is. Okay, so if I turn this on its side, you've got this oxygen which represents this. This oxygen represents this, and yet I've not put a bond in there because I'm quite lazy. I've just written this, and this represents that, and then this methyl group represents this. So this is kind of like what your monomer of your PMMA is. Okay. This is soluble in anisole. It's also soluble from acetone. So if you get the monomer, so if you get the PMMA and you buy it from, say, Sigma Ultra-Rich, I've done this a few times, you can put it in acetone and spin cast, and you get a nice film from it. The reason why we don't do that is because the volatility of the acetone is quite low, because it's got a low boiling point. You can do it on chips, like 1 centimeter squared. I've done that many times. You do a wafer, it looks ugly. So yeah, so when most people think about when they destroy their resist, it's basically destroyed in little bits. No. So when you strip your resist, there's still the molecule still intact. We've got ZEP here. So the way I look at ZEP, I always treat it in 2 different ways. So if we could ignore this chain length, these chains here, and we look at this monomer, we can see that this is the chlorine here, and then we've got this structure. Now again, we've got this like styrene is represented by this ethyl benzene here. Okay, so I break this into 2 when I model it into 2 parts. It's just easy to deal with. So essentially, this is what the parameters are, which I've used, and I'm working at 100 kilovolts and 1 million electrons, and we discussed why I use that, because repetition and how random is a random number. Not very. So okay, let's see what do these lines mean. So the black represents primary electrons, so they're the ones that be generated by your tool, and these secondary electrons and OJs are basically generated here. So the red represents the first order. The green represents the second order, which means that's the daughter of the first order secondary electron. Sorry, so that's the daughter of the reds. Then you get, I don't know if you can see that in there, but you get blues, and they're the daughter of the second order secondary electrons. That gets confusing, I know, but that's what it is. And then because these electrons need to get to ground, okay, so they need to go to the ground state. So usually for 100 kV, you need 4 orders of secondary electrons, and that's governed in purple, which I can't even see that. So take it from me, there's purple in there. And essentially, okay, so what does this mean? So what we can do is break this down, and we can look at like these molecules. Okay, so we've got a yellow one here. This is the secondary electrons, and this is the Augers. So we can see that at 10 kV, everything is going to come to us, which we expect that, 'cause there's a lot more interactions. But for 100 kV, and where I work, which is 30 kV, you can see it's a lot more sensitive than here. Right, okay, so we're looking at this guy. This guy is the most sensitive. So why am I showing you that? So if we've got ZEP and we put a bromine on there, or we put an iodide on there, the sensitivity will come to us, okay? Because there's a lot more secondary electrons in here that we can scatter off, and then they can generate, and we can also basically generate Augers from here. So basically your scattering goes up. If the scatter goes up, then the probability of interaction and ionizing and doing something with a resist improves. So the main question, I suppose, is, okay, if we know that this is better than this, then why don't we use it? And the answer is, as you go up in the periodic table, things become less soluble. And that's the problem. Otherwise, we just use gold. Or even though it's expensive, we probably could use bismuth or lead or mercury in my case. So, you know, this is not soluble. So if you can't spin cast it, then, because when you spin cast it, you need to have certain ratio of solids to the solvent to get the thickness that you want. Okay, so when you get this or these polymers, you weigh them out in a bottle, and then you weigh out your solvent, and then what you do is just basically put the solvent to the polymer, and then you put a magnetic stirrer, and you just stir it for maybe overnight, and then it completely goes transparent. These will go transparent, which means they're soluble. This will turn milky, which means they're just a sediment. So when you come to spin cast them, they'll look like a mess. So that's why we don't use them. Another tip is that you can go on Sigma Aldrich. You can buy this, weigh it out, do exactly what I just said. And then what you can do is when you go to dispenser on your silicon, use a filter. So it's anisole is what I recommend you use. Use a 0.2 filter, PTFE, okay? Because PTFE likes anisole. So don't use water on PTFE because it won't go through and you'll burst the filter. But 0.2, we filter it because we get rid of all the impurities. So that's what you can do. And this is where we're at. So essentially going back to this guy, we want to understand what's happening here, which I'll go through in massive detail in a minute, but we've got this monomer and we got this monomer, and as you can see, it's acting down here. So this is not very good. And we're going to explain why. So the amount of secondary electrons that this gets generated is when this gets broken down, because you can imagine you've got an electron here, electron there and there, and when you induce this, it just spins around in a circle until you smash this completely. So the energy associated to smash this is much larger. So what this role is when you generate secondary electrons from this and another species, which I'll go into in a minute, this acts like an absorber, and nothing absorbs. It basically comes to rest because the electrons are coming to rest. So the electrons basically get flown around here until they come to rest, but this is also getting annihilated as well. So it's kind of this is your sensitizer and this is your quencher, and that's how that works. but I'm going to go into huge detail what's going on here. Okay, so this is what we call a point spread function. A point spread function to me is not it's not straightforward. Okay, so when you've got tracer, you put your point spread function in. It's like this is the material and this is the energy. You shoot it in, and then you use that to do your proximity error correction. But when you do that, your proximity error correction is always underdosed. Why is that? Well, the reason why that is because this is a transient. Your material is undergoing a chemical change. So when you put one electron in, it does something. It changes the material. When you put another electron in, it sees that material change. So when you put another electron in, it sees the change of the electron of the change. So it ends up like a cascade, and you end up with this. So this is the material it starts with, and I've literally just made this up. Okay, so don't take this for gospel. I've literally just made this up because it's very complicated, which you're going to see in a minute. But this is very, 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 very. It could be many different possibilities of how this breaks. So essentially, we've got PMMA that we have here. We get the electron. It basically starts to break this down. We can generate a secondary electron. The same electron from the incident is still going through. This then changes. So this no longer looks like this. So we've got a methyl here, and the methyl up the top has basically disappeared. That can be turned into methane. So that can come out as a gas. So that's like an outgassing product, right? So that can diffuse through because you're giving it energy. And then you can generate more secondary electrons, and this breaks down even more. So you can basically get rid of this group, and you can end up with something much smaller. So when you've got a smaller product, your density usually increases. Okay, so I've literally just made this up, and I've looked at a PSF, but this is what a PSF is to me. So what you're looking at here. So I'm going to describe this. This is an energy deposition plot. So I'm taking the energies that are being generated by the primary beam. So I'm subtracting this. This is what this is. And then I'm basically looking about what their energies are, because that's what's important, because the energy change and what the direction is what's important, because I can work out where the bonds are being broken and at what point, at what time. And time is really important, right? Because this exposure is happening over time, right? So you can imagine this is decomposing, and this is why I've written decomposition there, meaning that if you think about your dose equation, you've got dose equals the time taken for it to have a chemical change multiplied by the current. So that's the amount of point charges you inserted in over the area. It's as simple as that. So that to me is what a point spread function really is. And so I've got a 50 nanometer thick PMMA layer here, and then I've got a silicon. So I've just taken this, and then I've basically transposed it and worked out what the energy is. Okay, so this is what it looks like. So when I play this, you can see that this is now undergoing a change, and then this change becomes huge. So the effect is much larger. So now we're looking at a percentage of the exposure of any particular layer. This is important because this undergoes a change, and this becomes a cumulative effect. Okay, so if I play this graph, you can see the amount of secondary electrons that are being generated. So you can see the silicon has a huge effect. Not a lot happens, and all of a sudden it just basically takes off. So again, I'm going to move myself, and we're kind of following this structure. So it kind of looks this line. It kind of looks linear, but when you look at it, it kind of isn't. So we can turn this upside down, and it kind of looks like this contrast curve a bit. Okay, so what you're seeing here is I'm repeating this every nanometer. So I'm making a change here. So my Excalibur knows that there's a chemical change, and it knows what level that was and what thickness. So I program what the thickness is, which is problematic. It's problematic because if I give you a ruler, and let's say it's a kilometer ruler, and I say, right, okay, let's be cruel. Let's measure the circumference of Australia. So you're going to come back after a few years and say, right, okay, the circumference is this number. I'll be like, okay. Then I'm going to be really cruel and say, right, I've got a millimeter ruler. Now do it. You'll come back in like a century or whatever, however long it takes. You'll come back to me and say, right, it's this number, and it has to be a very different number. So essentially what we've got is a fractal problem. So essentially this number governed here is dependent upon what this layer thickness is. So what we need to do is average across that in order to normalize that out. So essentially that's essentially where we are. So this is the work I did for my PhD in the early 2000s. So I'm taking PMMA 96K and then PMMA like almost a million K. You can see that the solubility is very different. Okay, but even though it has the same trend more or less. So you can see that from this percentage, if I turn this upside down, it can follow this. I haven't done that work just yet, but that's the conclusion where I'm hoping to get to. And this is the difference of the percentage of exposure. So essentially, this is kind of like what I wanted to show you really of how to think about what is that chemical change. Now, when you get into chemically amplified resist, then that's a whole different level of change. When you get into metal organics, you've got a lot more things going on. So, if you've got like tin and indium, these kinds of materials, then the change is more rapid. But as you can see, it all kind of follows this. So not a lot starts at the start because it needs time for it to gain inertia or overcome that force and start exposing this. Okay, so now we're going to talk about ZEP. So a lot of you asked Christopher Ober what's going on with ZEP. Last time I used this is with Guy DeRose a few years ago, but I've gone through this with you on what's happening here. This chlorine atom is very special. Christopher Ober basically pointed this out, and what happens is it's like I have here. So we can follow this through. I do have a picture of what happened, or a movie what kind of happens, but I'm making this up because any scattering can happen, and it's almost like a snowflake. There are no two snowflakes are the same, how this breaks down, which is why it's very complicated to model resists. So essentially, we've got this electron coming in, we're cleaving this bond, but we're also giving energy to this chlorine. This becomes what we call a free radical, or in the physics world, it becomes an ion that has charge. Okay, this charge allows this species to move around. This has got mass, and the material has got mass as well. So you're almost etching it. In fact, that's exactly what you're doing. It becomes like a dry etch inside your resist. So now you've got like your primary beam, you're generating secondaries, you're generating this chlorine, but it has a short life. Which is why you don't get a huge exposure. So what I'm showing you here is because of the work that we did with obviously Guy DeRose at Caltech, that we have a helium ion microscope. Okay, so you're no longer using electrons, you're using helium ions in order to expose the resist, which means that the distances that these things can travel is like over maybe a nanometer, 2 nanometers. So you can get really good resolution. But because you've got the mass, the sensitivity is like 10 microcoulombs per centimeter squared. So you can get like, you know, Guy and I were getting things like 5 nanometer half pitch at like 10 nanometer, 10 microcoulombs per centimeter squared. What's not to like? It's fantastic. I have no idea why it's not taken off, but that could be a marketing issue. But you know, that's what I think the future is. And you can see that going back to the ZEP, this chlorine starts breaking this down. And of course, when the electrons get trapped in the benzene ring, or the styrene as we call it, they basically just go in a circle and just essentially break it down. But it takes a lot of energy to break that down. So essentially, this is the algorithm which I've written for you here. So you know, has an instant electron collided with a chloride? Yes. Okay. It's now part of the exposing particle as well. So that's now an ion. So we need to calculate the mean free path, and we all know how to do that because we just did it. Calculate the scattering angles. We know how to do that. So now we need to do something which is a little bit different. So we need to find the stopping powers. So we know how to do the electronic one. We've done that. But because it's got mass, it's got nucleus, we need to understand what the nucleus stopping power. So this becomes dominant as certain regimes within energy regimes. Okay, so at high energies, it kind of flies through that, but at low energies, it becomes more prevalent. And then that becomes a huge knob to turn, which is fantastic for what we do. Then we need to calculate the secondary electron yield. So how many electrons are going to be generated every time it collides with something or from itself? And this is huge. And you can see here in red. So this is the first order. There are third, second, and fourth orders in there, or second, third, and fourth orders, whatever. But you don't see them because they're covered by the red. So you can see it's a huge explosion. So what I've done here is used a chlorine ion at 35 kilovolts, and just basically I've got rid of these that's happening here. Otherwise, it just becomes a sea of red, and you don't the message gets diluted. So I've got chlorine atom, and this is going into PMMA, and then you get this huge explosion. That's what's going on. So you can see the effect really. And then essentially we come back and then just go again. And then we just do this in a loop. Okay, so now we need to understand how ions behave. So what I've actually done is we can use this as a you can use it as a case study for dry etching as well. But yeah, essentially we need to understand the probability of causing an ionization. We need to work out what the cross section is, which we've got here, and we can just play that through. We need to find the scattering angles, and we need to find the nuclear and electronic stopping power. So it's governed by these equations, which is we've got the electronic one on here and the nuclear one on there. So you can see that, and you can work through that. And then this is the final slide, I guess, that we go through this phase. So the last one we had 3, I just decided to do 4. So we play that. This is what it looks like. So you can see that it's getting its exposure, but it's actually changing as well. So it's getting more. This is what it looks like. So I've slowed this down a lot. So you can see that how this kind of breaks down. So we've got the chlorine ion behaving and how they're secondary electrons and how this now is more soluble. And then if I play this, you can see that it gets very slow, and then all of a sudden it starts to race off. Okay, so as the percentage increases, and then we still kind of have this characteristic. So this is the work that was done with Guy at Caltech, and this is what we ended up getting. These are exposure conditions. And then, this is just a resolution. So this is what we ended up with. So we all know what it can do. Then I'm showing you something that Guy and I developed, was this one naphthyl methacrylate. So we put 2 here. So it enhances the dry etch performance because the benzene rings, as you now know, takes a lot of energy to smash. So if you've got 3 or 4, you can have pyrene or anthracene or whatever, the dry etch selectivity goes up. But that comes at the expense of sensitivity, as you can see here. Right, so the last slide, we can see that the takeaway is you get a dry etch selectivity of 1:1 with PMMA, no surprise there. 2:7, this is a silicon dry etch. And I've got the space to put the parameters of what we used, but they're in our papers. We got 2.7, and you can see that it's actually done its job, and got 3.8 to 1, which is nothing to shout home about, to be fair. Guy and I've got resists have got like hundreds, which you'll find out in March. We'll show you resist that got dry etch activities that you can all try that are hundreds to 1 here for silicon. And these are my team, or the people I work with. So Richard's the organic chemist that I work with. These are the guys at Manchester. This is my group. These are my PhD students, and that's me, of course. This is Yasin at Switzerland. Kevin Lister, who's mine and Guy's business partner. Louisa, at a very good friend of mine at Applied Materials that we do a lot of work with, and Dario at IBM did a lot of work with EUV. And then Guy DeRose, who's here somewhere, so you can ask him. And if you look at Hayden was my ex-PhD student, but if you go on the web, you can find his thesis and everything's in there. Okay. And thank you for listening to part 1.